And hi, so yeah, I want to talk about how I transform, how the journey was like in COVID, where the research dissertation had to be transformed from something experimental and theoretical, or rather simulation, to like full-time simulation work. And I'm going to be discussing my master's thesis. Now before I do that, I just wanted to show you some bits of how CIET worked. Okay, so let me show you some pictures. This is like the first and second floor of CIET. So it says this is the compact integral effects test. As you can see here, compact integral effects test, and this long thing right here, this is the heater. This is the heater. Okay, let's see whether I can have any editing tools. Rotate, share, browse. Nah, okay, never mind. Maybe I should just use the crop. Nah. Alright, so this is where the heater is, this red thing right in the center that goes all the way to the bottom. Okay, so that's how fluid flows through the heater branch. Okay, there are some other bits of piping as well. So the pump for CIET, this is the pump right over here. You are barely able to see it. Okay, you won't. It's not very easy to see. Okay, and the electrical supplies for this heater, 10 kilowatt heater, are in this black cable insulation right here, right at the bottom. Okay, this black cable right here. So at that time, it was only possible to heat this heater up with only 10 kilowatts of power. Now you may be wondering what are all these little wires around. These are thermocouple wires, temperature sensor wires. So these will feed information in real time to the what we call the data acquisition system, or DAC. It is also called the PIC. Okay, it is called the PIC, and this is what the PIC actually looks like. So the first floor of CIET is what you see behind this computing system here, and all these wires will be fit into the PIC right here. Alright, it'll fit into the PIC right here, and it's supposed to be connected to the computer via some LAN cable and router. So there was some IP address architecture I had to look into to try and debug this. Okay, so there were flow meters. Okay, there were flow meters, right? Okay, if you can see here, this is the same level 1 I was talking about. Okay, there are flow meters. These are the turquoise flow meters. Okay, the flow meters are here. These are the flow meters. They are Siemens Coriolis flow meters. So there are 3 over here, and they are there to deal with fluid flow in each branch. Okay. Excuse me. So this is if you can see the numbering here, it looks like 60 or something like that. So these are the, was it 40? I can't really see it from here. But this is the flow meter that actually measures flow through the pump, okay, through the pump manifold area and the coiled tube air heater. So it measures flow for the forced circulation side. This flow meter here measures flow through the, I believe it's the heater. Is it the heater? No. This is not going through the heater. This is going through the what we call the bypass valve. Okay, the bypass valve. This is not modeled in my CIET educational simulator because a lot of the experiments don't deal with this branch. So this is the part, the simplification I ignore, and this part is to deal with the DHX, direct heat exchanger loop, that deals with the natural circulation part of CIET. What else? Okay, so you can see this context here. These are actually where the current is flowing through to actually electrically heat the terminal VP1. And now you may ask yourself what these tubes are. Okay, these tubes are actually for manometer lines. They are for pressure measurements in the compact integral effects test. Okay, and then all these valves and pipes here are meant to be open when there's a draining and filling procedure. So either when you want to drain the whole compact integral effects test of its what do you call that? Of its fluid, the diaphragm A, and it has to go into a drain tank or something, it will be via these pipes here. So that's it. For flow meters, the indicators are over here. Okay, the Drex flow, the Cheetah flow. You can see the Drex flow here. These are Siemens Coriolis flow meters. They are currently powered off. Okay, and these are the 4 loops. Okay, so 3 of them are for the main loop, the primary loop, one for the natural circulation site or the DHX branch, one for the Cheetah branch, which is what we call the forced circulation site. The last one is for the bypass valve. That one is not modeled inside my CIET educational simulator. Okay, the CIET educational simulator is my actual eventual digital twin of this, or the simulation, the real-time simulation. Then we have the Drex loop for the natural circulation part also. This is the second part of the natural circulation part. Okay. Now, I've gone on enough about CIET as well. Okay, one more thing. These what we call the VFDs, variable frequency drives. They control 3 things. Okay, one is the pump, which controls the speed of the pump impeller or blade or whatever they call. Okay. The second is for the TCHX. Okay. Thermal siphon cool heat exchanger. Basically, it's one of the fans that cools the natural circulation side of the CIET. And the Cheetah, coiled tube air heater. This one is responsible for the forced circulation side of CIET. Okay, so all these flow meters, the flow meters are here. For example, FM40 right here. Flow meters, variable frequency drives, and all the thermocouples will pipe their information into this PIC-C, and then it will go through the computer via a LAN cable. And the computer, back then when I was in Berkeley, it was called ARCO, Advanced Reactor Control and Operations. Yeah, you see, Advanced Reactor Control and Operations. So it says experiment in progress, restricted access. That's just what we left down there, and some security mirror as well we had. So this was the lab in UC Berkeley called 1140. Just for information, we actually had, in UC Berkeley we used to have a nuclear reactor, experimental nuclear reactor room with an actual nuclear reactor, but it's no longer there anymore. So that's why this reactor operator thing is here. Okay, that's just a relic of the past. It's not there anymore. So I mean, there are traces of radioactivity, but it's hardly of any concern. I spent a lot of time down there. Could barely get any trace of radioactivity that was at a concerning level. Anyway, so I've yapped on enough. Let me go through my master's thesis. So for this real-time simulation of CIET, the compact integral effects test, there are 2 main parts I had to simulate. One is the fluid mechanics, and then the other part's the thermal heat transfer. So for the heat transfer specifically, it talks about conduction, convection, and radiation. But radiation is so negligible here that it can be ignored. So it's just mostly conduction and convection. Fluid mechanics is the more important bit. Okay, it's the first batch of problems I had to settle, and that's where my master's thesis actually came about. Okay, how do I tackle this fluid mechanics problem? Okay, this was my master's thesis, which I'm going to show you now. And I'm going to walk you through it. Okay, I'm not going to publish it online because it's actually supposed to belong in the UC Berkeley library. Okay, so I'm not going to upload it, but I'm going to go through the important parts of it and summarize it for you. So, so this is my master's thesis. It was guided by these professors right here. Okay, my professors Per Peterson. one of his ex-students was Reluca Scarlett, but she graduated and became a professor herself, and she guided me. She's really, really good, very thorough. I learned a lot from her. Okay, so this is Professor Scarlett, and the new thermohydraulics professor, Professor Peterson, I think he was going to do more work at Kairos Power. So in the UC Berkeley Nuclear Engineering Department, a new thermohydraulics professor was coming in, and this is Professor Kwan Yi Su. Okay, so I finished my dissertation in spring 2023, about May 2023. Okay, so it says here development of an isothermal flow. Isothermal means constant temperature, no heat transfer there. Okay, isothermal flow digital twin for the compact integral effects test. Okay, here are some of the important pointers. This is the abstract. Okay, so I went through the bits. I went through the bits earlier. Okay, let me see. Freehand line, yeah. I went through the bits earlier, and I was justifying why I was constructing this real-time simulation or digital twin. So this digital twin of CIET was motivated because it can be removed. It can be used for a lots of things like remote operation studies, fault detection studies, operator training studies. So if you had a simulation, you can actually train people on it if your simulation is realistic enough. So what I actually want to highlight here is that the COVID-19 pandemic was actually what made this digital twin construction so essential, because experiments were nearly impossible. So I wanted to make this real-time simulation that can simulate CIET on a desktop computer. Okay, of course that time open source software for constructing this was very limited. Was very limited. So I could not do anything back then. A lot of the software is proprietary and export controlled, like Relab, and Modelica just didn't really make the cut. There are lots of other libraries. Okay, so I was running into walls, and I was trying to see, okay, if the software, open source software was lacking, and of course the proprietary software wasn't quite good for me because it's export controlled. What can I do in terms of open source software? So I had to write it up using Rust. Okay, and why I use Rust? That is what I wrote in this dissertation, or this master's thesis. Okay. So well, the thing with this isothermal digital twin is that I wanted to use it as a baseline to construct the full digital twin with actual heat transfer capabilities. So this was not even completed during my PhD, but I have actually completed it now. So I can show you what the end result is like after many years. Okay. So example, CIET educational simulator. So I'll let it compile in the background. Okay, actually, do I have oops, I don't have it. I'll let this thing compile, but I'll show you what the digital twin is like when it's done. So what was my thesis like? Okay, I talk about motivation, which I already covered. So this part, I actually look into literature of what digital twins are. How do I define it? Unless you're really interested in digital twins, this part I kind of skip. Okay. Okay, so next thing which is more interesting is this methodology, especially 3.2 when I talk about operator splitting. Okay, so what I want to do is to achieve real-time calculations for fluid mechanics and heat transfer. Okay, then I talk about solution procedure for parallel branches in the flow. I talk about choice of coding language, and what is this OPC UA server and client. Okay, and then after making this isothermal digital twin, of course, yeah, I need to do this code validation. I made some approximations to simplify my situation, and then most importantly, when I talk about having real-time simulations on a PC, like not a supercomputer. I needed to test it on actual hardware, so I tested it on some of my laptops there. Okay, so these are some of the important results and discussion, how well this digital twin performed, and the conclusion. So this thing took about a year plus, this itself, but it was not the full suite. Okay, this is the full suite of what the digital twin in CIET looks like. Okay, so I had the heater, but you know, my first few iterations of CIET did not have that. Okay, the only thing in this master's thesis was to deal with the forced circulation here. Okay, because it's isothermal, there is no way that heat will be transferred, so there's not going to be any natural convection. Okay, so if I turn on the pump, there will be and I adjust the pump to some pressure, okay, to exert some pressure on the fluid, I'm able to then come up with this flow rate here. Okay, if I do a reverse direction, it can also have a different kind of flow rate. Okay, and this pump flow rate here, FM20, it actually measures flow through the Drex loop on DHX branch. Okay, yeah, it will measure flow rate here. So how I constructed this, then I will have to go through step by step. Okay, but I'll just let this simulator run. Okay, this was you know, the whole outcome of my dissertation work, and then a little bit more after, where I published my results in a paper called TWAS. Okay, where I finished up this simulator. Okay, so actually I did yeah, so this is the results. These are the results. A lot of appendices. So yeah, credits and acknowledgements later. You know, I mean, I have to, of course, thank the people in my lab for doing it. People who supported me. Okay, over the time. So all of this people I do want to give credit to, and of course, yeah, I found one of my lab mates is from the LDS Church, the LDS, Latter-day Saint Church. He also gave credit to God, and I also do the same here. Okay, I'm not LDS, I'm a Christian, but okay, yeah, that's what I did. Okay, so these are credits. It's always good to be thankful for help received along the way. Okay, and that's very important. Okay, so introduction I kind of skip because I spent the last few videos talking about that. Okay, so again, my end goal was to make a digital twin of the compact integral effects test. Okay, and I based it on the models that people had online. So this is my conceptual model. I drew it using OpenOffice, or rather LibreOffice. Okay, so what you have in CIET, remember, it's the electrical heater. It will send heat through into the terminal VP1, and you will actually have a pump that's pumping fluid throughout the system. All right, and then it goes into the heater branch, goes out here, and it goes through all the way around. Okay, so to ensure that the components are coded correctly, of course you need to perform some preliminary tests, and the first few tests do not actually deal with the heater right here. Okay, so this part talks about some difficulties in doing CIET. As mentioned before, there are the safety requirements that always mandate 2 people operate CIET in any time in case of a hot oil spill. Okay, so you know, I need to make sure schedules are planned in advance, so on and so forth. I already shared this before, I'm not going to do again. Here is me justifying why there should be a digital twin of CIET, and these are definitions of digital twins, which I am going to skip. I actually repeat this part in what do you call it, in my PhD dissertation, kind of emphasizing it. So So artificial intelligence training, okay, operator training, yeah. So the nice thing about having this simulator is that once you have it, you can train people how to operate the system. Okay. So I'm gonna skip this part. And then go down here. Right. So now I want to talk about, re-emphasize how the compact integral effects test, or CIET, actually works. So remember, we have the control elements here, the variable frequency drives, the flow meters, and they will pipe information into the so-called PIC, and this will pipe information into the advanced reactor control or operation. All of this is in the CIET plant site. Okay, this is in the CIET plant site. So the local operations like that was what happened. Now, if you so-called want to control it remotely, and that was part of the research done in my lab before. Okay, what happens is that this is like a remote server. Okay, so this is like a remote server, and it will send its information into a client, okay, using the OPCUA protocol. This is like HTTPS. So this is basically like HTTPS for the Internet of Things, IoT. Okay, used for industrial code as well, industrial control systems. Okay, so basically, if you want to operate CIET, you can also do it using a remote server client interface, and that was what I was looking to replicate as well. So it's a huge effort. So right now, I'll just focus on this site, the CIET plant site. Okay. So the thing about the requirements is that the calculations for CIET must be extremely fast. Okay, extremely fast. How fast? Okay, from CIET itself, the control system of CIET, it actually refreshes itself every 95 to 100 milliseconds. So this is about 0.1 seconds. So basically, to have a very smooth and seamless experience for the end user, all calculations should be done within this time frame. Okay, for every time step, every time you want to refresh the system, the calculations should be done within this 0.1 seconds. Okay, so that's the benchmark I'm aiming to have. Okay, and there are some simplifications I use. To simulate the pumps, I actually kind of simplified the whole thing. So it's just to give people a feel of what CIET is like. Okay, so I actually simplified the interaction with the pump. Okay, so on and so forth. And for this master's thesis, I only dealt with the isothermal flow. That means flow at a constant temperature. Okay, then over here, well, maybe I'll come back here when I look at open source libraries for writing a digital twin server. Okay, so before I do that, let me come back to here. So this one I'll skip. Okay, libraries, yeah, methodology, yes. So basically, inside my my master's thesis, I was experimenting, and I wanted to replicate the remote control architecture that Arco CIET had. Okay, so CIET, the plant site, I have the plant site on one end, which it compiles the information and pumps it to a OPCUA server, and you can access it from a OPCUA client. Now I wanted to have everything here. So for the server side, I actually used some sort of a PC, okay, some sort of a PC, and I had to learn how to wire this up to a router, okay, so that I can replicate what goes on in CIET. So I was learning a lot of networking, IP address and everything as well. Okay, a lot of networking. And then the OPC UA client. Okay, OPC UA client is just going to take information from this server through the router. So this is like a local Wi-Fi system. So it is taking information from there, from this server, and this client is a totally different computer, and it uses a Python OPC UA graphical user interface client. Okay, the input and output you can just key things in through the computer on a different computer. So this is the whole setup I was going for. Okay, so what do you need to solve in fluid mechanics? Okay, so let me see. Okay, now I'll just use this one here. So for fluid mechanics, basically, let's say this is engineering 101. Let's say you have a series of pipes, right? And they are connected in series. Okay, so to solve for fluid mechanics, there are two kinds of balances we need to solve. One is the mass balance, which basically says mass cannot be created or destroyed. It has to flow from one point to another. Okay. Second of all, it's the momentum balance. Okay, so a fluid will flow from here, and let's say the fluid, let's say it's water or the coolant or whatever, is at some pressure A. It will flow through these pipes, and the friction in the pipes will cause this fluid to lose energy. Okay, it will cause this fluid to lose energy. Now when something loses energy, let's say you have a ball, or you're running across, you are pushing a cart across a field. Okay, you're pushing a cart across a field. Okay, when you go this way, the friction is actually pointing the other way. Okay, and you actually lose energy. So when you lose energy, you are taking the energy out of the cart, and the cart is slowing down. So for a cart that is going to, let's say, the right, it will lose energy by slowing down. Now for fluids, there's a bit of a problem. Okay, if you have pipes of the same dimension, for example, if you have, let's say, a mass flow rate coming here called M1. Okay, if there are no leaks or anything, okay, if there are no leaks and the fluid isn't getting stored into the pipe, and it's just water going through these pipes, or it can be oil as well, and basically you cannot compress the fluid, and it doesn't really change density. So if you have fluid flowing through the pipe, if fluid flows in at a mass flow rate of M1, the amount of mass coming out of this series of pipe must also be M1, because conservation of mass. So if the conservation of mass applies, it also means that the velocity, okay, if the conservation of mass applies and the density is the same, and the cross-sectional area is the same, okay, what happens is that if fluid flows from the pipe from this point A to point B, all right, the velocity is the same. Okay, the velocity is the same. Okay, the mass flow rate must be the same, and the and under special conditions the velocity is the same as well. So where does the energy actually drop out? Okay, it drops out by reducing the pressure. So the energy that is lost through this pressure right here, this PA. So when the fluid flows out at PB, okay, the pressure is a lot less or somewhat less than PA. Okay, and you can find lots of these online through what you call the Darcy-Weisbach equation. Okay, so this what I just described to you is what we call head loss, energy loss due to friction in a pipe flow. Okay, there are other kinds of losses as well, but a lot of them have to do with the friction in the pipe. So momentum balance, yes, sure, you kind of have the same mass flow rate and the same velocity, but this momentum balance actually also will tell you that the pressure of the pipe is actually lost. Okay, pressure of the fluid is actually lost as the fluid flows through the pipe. Okay, if there's not enough pressure differential, the fluid will just get stuck in the pipe. All right. So yeah, so this is the mass and momentum balance for a series of pipes. So let's say we have this pressure loss. Okay, how is it being calculated? Okay, it's actually calculated through the Darcy-Weisbach equation. This pressure loss is actually proportional to half rho u square. So this is what we call the dynamic pressure, half rho u square. There's dynamic pressure, and then you have this combined loss term, which is the foam loss plus the frictional losses. This F Darcy is the Darcy friction factor or the frictional losses. This K here is the foam loss coefficient. And all of that's described in my dissertation or the thesis right here. Okay, the Darcy-Weisbach equation. So each pipe will have a particular loss coefficient. Each pipe will have a particular loss coefficient. Okay, half rho u squared times the whatever is inside. So this you have it for this pipe, you have it for this pipe, you have it for this pipe. Basically, all the components within any branch or any piping system, where a branch is you have many pipes or many fluid components connected in series. Okay, all of them will have this sort of pressure losses. Okay, and the way, okay, of course, sometimes I like to actually calculate things in terms of mass flow rate. So this equation is the same equation that over here, except I rather write it in terms of mass flow rate here, rather than using the velocity, which can change based on the cross-sectional area. So what I'm interested here is in the mass flow rate. Okay, so this is the pressure loss correlated to the mass flow rate going through the pipe. Okay, so this Darcy friction factor, if you studied undergraduate chemical engineering or even mechanical engineering, you should know this is actually determined through the Reynolds number using the this Darcy-Weisbach friction factor. So you have to read things off this chart, which they are not showing me now. Okay, now you can show, yeah, they are showing. So this is called a Moody chart or Moody diagram. Okay, a lot of engineering toolboxes will have it online. This is basic chemical engineering, so I'm not going to do it. Not going to do anything. So for a series of pipes, okay, the pressure loss is equals to the sum of, okay, the sum of delta P loss in each component. Okay, so each component will have some kind of loss terms determined by this Darcy-Weisbach equation. So this is what I call the I. Okay, let's see whether I can use an erasing tool. Okay. Maybe let me pause. Okay, but never mind. Never mind, I'll just leave it as that. So, to solve this Darcy-Weisbach equation, there needs to be a sort of iterative approach. A sort of iterative approach where basically I'm guessing from this equation here, there's going to be a certain pressure loss, let's say 1000 pascals, for example. Let's say this pressure loss is 1000 pascals. The solution procedure will be to take these loss terms, okay, the half rho m dot square over rho a square, and then times whatever is inside, and then I sum them up. Okay, so this is the sort of equation we are dealing with. Okay, so basically what I do is I try to guess the mass flow rate here, and based on the mass flow rate, I should be able to, based on many guesses of the mass flow rate, I should be able to guess and check. Maybe my first guess of the mass flow rate gives me 950 pascals. The next guess is 1050 pascals, and I keep guessing back and forth until I make sure that the mass flow rate here is the correct mass flow rate that gives me the loss term of 1000 pascals. Of course, if things were simpler, let's say if let's say this term here was constant, we won't even have to do this guessing back and forth process. Okay, unfortunately that's not the case. For actually this Darcy friction factor is equals a function of the Reynolds number, and this Reynolds number is actually a function of the mass flow rate. Okay, and it's not a simple function. You have to use that Darcy-Weisbach equation. It's not a linear function. It's not so simple. So basically the only way to effectively solve this is that I use this iterative approach that allows me to solve for the pressure drop equation within a series of components. So that's the part about my PhD, the first part that I was thinking about. Alright, in this series of pipes. I'm not going to explain too much because this is a more in-depth engineering part. I hope you know a bit of fluid mechanics. If not, you can be half stuck here. Okay, but that's what I was doing first, and then okay, I'll stop this, and then I'll continue next time.